it'll be easier to correct bias in algorithms, because I feel like you still need people kind of making the decisions to prioritize that. Like it requires kind of an overhaul of the system's priorities, I think.
It also starts with the premise that there are people who can't be fired or disciplined or whatever,
Yeah.
which I guess maybe for some judges that's true, but that kind of maybe suggests that judges shouldn't be lifetime appointments.
Yeah, because I mean, even then, I think you kind of need the change of heart of the people advocating for the new system, which I think can would be necessary in other case, kind of, and that's kind of the critical piece of getting the people that are wanting to overhaul the values of a system. So returning to this issue of the Rohingya genocide, and this is a kind of continuing issue. This is something that's just kind of really stunning to me that there were so many warnings and that so many people tried to raise an alarm on this, and that so little action was taken. And even this was last year, Zuckerberg finally said that Facebook would add, or maybe this was probably 2 years ago, said that Facebook would add, but this is, after genocide's already happening. Facebook would add dozens of Burmese language content reviewers. So in contrast, so we have this is how Facebook really failed to respond in any significant way in Myanmar. Germany passed a much stricter law about hate speech, NetGG, DZ, and the potential penalty would be up to like 50 million euros. Facebook hired 1,200 people in under a year because they were so worried about this penalty. And so, and I'm not saying that like this is a law we want to replicate. Here, I'm just illustrating the difference between being told that you're contributing or playing a determining role in a genocide versus a significant financial penalty. We have seen what the one thing that makes Facebook take action is. And so I think that is really significant in remembering what the power of a credible threat of a significant fine is, and it has to be a lot more than just like a cost of doing business. So I really believe that we need both policy and ethical behavior within industry. I think that policy is the appropriate tool for addressing negative externalities, misaligned economic incentives, race to the bottom situations, and enforcing accountability. However, ethical behavior of individuals and of data scientists and software engineers working in industry is very much necessary as well, because the law is not always going to keep up. It's not going to cover all the edge cases. We really need the people in industry to be making kind of ethical decisions as well. And so I believe both are significant and important. And something to note here is that many examples of kind of AI ethics issues, and I haven't talked about all of these, but there was Amazon's facial recognition. The ACLU did a study finding that it incorrectly matched 28 members of Congress to criminal mugshots, and this disproportionately included Congress people of color. There's also, this was a terrible article, not the article was good, but the story is terrible, of a city that's using this IBM dashboard for predictive policing, and a city official said, oh, like whenever you have machine learning, it's always 99% accurate, which is false and quite concerning. We had the issue in 2016, ProPublica discovered that you could place a housing ad on Facebook and say, like, I don't want Latino or Black people, or I don't want wheelchair users to see this housing ad, which seems like a violation of the Fair Housing Act. And so there's this article, and Facebook was like, we're so sorry. And then over a year later, it was still going on. ProPublica went back and wrote another article about it. There's also this issue of dozens of companies were placing ads on Facebook, job ads, and saying like, we only want young people to see this. There's the Amazon creating the recruiting tool that penalized resumes that had the word women's in it. And so something to note about these examples, and many of the examples we've talked about today, is that many of these are about human rights and civil rights. And it's a good article by Dominique Harrison of the Aspen Institute on this. And I kind of agree with Anil Dash's framing. He wrote, there is no technology industry anymore. Tech is being used in every industry. And so I think in particular, we need to consider human rights and civil rights, such as housing, education, employment, criminal justice, voting, and medical care, and think about what rights we want to safeguard. And I do think policy is the appropriate way to do that. And I think, it's very easy to be discouraged about regulation, but I think sometimes we overlook the positive or the cases where it's worked well. And so something I really liked about Data Sheets for Data Sets by Timnit Gebru et al. Is that they go through 3 case studies of how standardization and regulation came to different industries. So it's the electronics industry around circuits and resistors. And so that's kind of around the standardization of, what the specs are and what you write down about them. The pharmaceutical industry and car safety. And none of these are perfect, but it's still, it was a kind of very illuminating, the case studies there. And in particular, I got very interested in the car safety one. There's also a great 99% Invisible episode. This is a design podcast about it. And so some things I learned is that, early cars had sharp metal knobs on the dashboard that could lodge in people's skulls in a crash. Non-collapsible steering columns would frequently impale drivers. And then even after the collapsible steering column was invented, it wasn't actually implemented because there was no economic incentive to do so. But it's the collapsible steering column has, they said, saved more lives than anything other than the seatbelt when it comes to car safety. And there was also this widespread belief that cars were dangerous because of the people driving them. And it took consumer safety advocates decades to just even change the culture of discussion around this and to start kind of gathering and tracking the data, and to put more of an onus on car companies around safety. GM hired a private detective to trail Ralph Nader and try to dig up dirt on him. And so this was really a battle that we kind of I take for granted now, and so kind of shows how much it can take to change the needle there. And then a kind of a more recent issue is that it wasn't until I believe 2011 that it was required that crash test dummies start representing the average female anatomy, in addition to. Previously, it was kind of just crash test dummies were like men, and that in a crash of the same impact, women were 40% more likely to be injured than men because that's kind of who the cars were being designed for. So I thought all this was very interesting, and it can be helpful to kind of remember some of the successes we've had. And another area that's very relevant is environmental protections, and kind of looking back and Maciek Seglowski has a great article on this, but just remembering, like in the US, we used to have rivers that would catch on fire, and London had terrible smog, and that these are things that were would not have been possible to kind of solve as an individual. We really needed kind of coordinated regulation on. All right, and so then on a kind of closing note, so I think a lot of the problems I've touched on tonight are really huge and difficult problems, and they're often kind of very complicated. And I go into more detail in this in the course, so please check out the course once it's released. I always try to offer some like steps towards solutions, but I realize they're not always as satisfying as I would like. Of like, this is going to solve it, and that's because these are really difficult problems. And Julia Angwin, a former journalist from ProPublica and now the editor-in-chief of The Markup, gave a really great interview on privacy last year that I liked and found very encouraging. She said, "I strongly believe that in order to solve a problem, you have to diagnose it, and that we're still in the diagnosis phase of this." If you think about the turn of the century and industrialization, we had, I don't know, 30 years of child labor, unlimited work hours, terrible working conditions, and it took a lot of journalists muckraking and advocacy to diagnose the problem and have some understanding of what it was, and then the activism to get laws changed. I see my role as trying to make as clear as possible what the downsides are and diagnosing them really accurately so that they can be solvable. That's hard work, and lots more people need to be doing it. And so I found that really encouraging, and that I do think we should be working towards solutions, but I think just at this point, even better diagnosing and understanding kind of the complex problems we're facing is valuable work.
A couple of people are very keen to see your full course on ethics. Is that something that they might be able to attend or buy or something?
So it will be released for free at some point this summer. And it was there was a paid in-person version offered at the Data Institute as a certificate, kind of similar to how this course was supposed to be offered, in person. The data ethics one was in person, and that took place in January and February. And then I'm currently teaching a version for the Masters of Data Science students at USF, and I will be releasing the free online version, later, sometime before July. Thank you. I'll see you next time.
Hi, everybody, and welcome to Lesson 6. Where we're going to continue looking at training convolutional neural networks for computer vision. And so we last looked at this the lesson before last, and specifically we were looking at how to train an image classifier to pick out breeds of pet, one of 37 breeds of pet. And we'd gotten as far as training a model, but we also had to look and figure out what loss function was actually being used to train this model. And so we talked about cross-entropy loss, which is actually a really important concept. And some of the things we'll talk about today depend a bit on you understanding this concept. So if you were at all unsure about where we got to with that, go back and have another look, have a look at the questionnaire in particular, and make sure that you're comfortable with cross-entropy loss. If you're not, you may want to go back to the 04 MNIST basics notebook and remind yourself about MNIST loss, because it's very, very similar. That's what we built on to build up cross-entropy loss. So having trained our model, the next thing we're going to do is look at model interpretation. There's not much point having a model if you don't see what it's doing. And one thing we can do is use a confusion matrix, which in this case is not terribly helpful. There's kind of a few too many. I mean, it's not too bad. We can kind of see some colored areas. And so this diagonal here are all the ones that are classified correctly. So for Persians, there were 31 classified as Persians. But we can see there's some bigger numbers here, like a Siamese. 6 were misclassified. They're actually considered a Burman. But for when you've got a lot of classes like this, it might be better instead to use the most confused method. And that tells you the combinations which it got wrong the most often. In other words, which numbers are the biggest. So actually here's the biggest one, 10. And that's confusing an American Pit Bull Terrier or a Staffordshire Bull Terrier. That's happened 10 times. And a Ragdoll is getting confused with a Burman 8 times. And so I'm not a dog or cat expert, and so I don't know what this stuff means. So I looked it up on the internet, and I found that American Pit Bull Terriers and Staffordshire Bull Terriers are almost identical, but I think they sometimes have a slightly different colored nose, if I remember correctly. And Ragdolls and Burmans are types of cat that are so similar to each other that there's whole long threads on cat lover forums about, is this a Ragdoll or is this a Burman, and experts disagreeing with each other. So no surprise that these things are getting confused. So when you see your model making sensible mistakes, the kind of mistakes that humans make, that's a pretty good sign that it's picking up the right kind of stuff, and that the kinds of errors you're getting also might be pretty tricky to fix. But, let's see if we can make it better. And one way to try and make it better is to improve our learning rate. Why would we want to improve the learning rate? Well, one thing we'd like to do is to try to train it faster, get more done in less epochs. And so one way to do that would be to call our fine-tune method with a higher learning rate. So last time we used the default, which I think is, there you go, 1e neg 2. And so if we pump that up to 0.1, it's going to jump further each time. So remember the learning rate, and if you've forgotten this, have a look again at notebook 4. That's the thing we multiply the gradients by to decide how far to step. And unfortunately, when we use this higher learning rate, the error rate goes from 0.08 in 3 epochs to 0.83. So we're getting the vast majority of them wrong now. So that's not a good sign. So why did that happen? Well, what happened is rather than this gradual move towards the minimum, we had this thing where we step too far and we get further away. So when you see this happening, which looks in practice like this, your error rate getting worse right from the start, that's a sign your learning rate is too high. So we need to find something just right. Not too small that we take tiny jumps and it takes forever, and not too big that we either get worse and worse, or we just jump backwards and forwards quite slowly. So to find a good learning rate, we can use something that the researcher Leslie Smith came up with called the learning rate finder. And the learning rate finder is pretty simple. All we do, remember when we do stochastic gradient descent, we look at one mini batch at a time, or a few images in this case at a time, find the gradient for that set of images for the mini batch, and step our weights based on the learning rate and the gradient. Well, what Leslie Smith said was, okay, let's do the very first mini batch at a really, really low learning rate, like 10 to the minus 7. And then let's increase by a little bit, so like maybe 25% higher, and do another step, and then 25% higher and do another step. So these are not epochs, these are just a simple mini batch. And then we can plot on this chart here, okay, at 10 to the minus 7, what was the loss? And at 25% higher than that, what was the loss? And at 25% higher than that, what was the loss? And so not surprisingly, if you do that at the low learning rates, the loss doesn't really come down, because the learning rate is so small that these steps are tiny, tiny, tiny. And then gradually, we get to the point where they're big enough to make a difference, and the loss starts coming down, because we've plotted here the learning rate against the loss, right? So here, the loss is coming down as we continue to increase the learning rate. The loss comes down until we get to a point where our learning rate's too high. And so it flattens out, and then, oh, it's getting worse again. So here's the point above like 0.1, where we're in this territory. So what we really want is somewhere around here, where it's kind of nice and steep. So you can actually ask it the learning rate finder. So we used LR find to get this plot. We can get back from it the minimum and steep. And so steep is, where was it steepest? So the steepest point was 5e neg 3. And the minimum point divided by 10, that's quite a good rule of thumb, is 1e neg 2. So somewhere around this range might be pretty good. So each time you run it, you'll get different values. A different time we ran it, we thought that maybe 3e neg 3 would be good, so we picked that. And you'll notice the learning rate finder is a logarithmic scale. Be careful of interpreting that. So we can now rerun the learning rate finder, setting the learning rate to a number we picked from the learning rate finder, which in this case was 3e neg 3. And we can see now that's looking good, right? We've got an 8.3% error rate after 3 epochs. So this idea of the learning rate finder is very straightforward. I can describe it to you in a couple of sentences. It doesn't require any complex math. And yet it was only invented in 2015, which is super interesting, right? It just shows that there's so many interesting things for us still to learn and discover. I think part of the reason perhaps for this, it took a while, is that, engineers kind of love using lots and lots of computers. So before the learning rate finder came along, people would run lots of experiments on big clusters to find out which learning rate was the best, rather than just doing a batch at a time. And I think partly also the idea of having a thing where a human is in the loop, where we look at something and make a decision, is also kind of unfashionable. A lot of folks in research and industry love things which are fully automated. But anyway, it's great we now have this tool because it makes our life easier. And FastAI is certainly the first library to have this, and I don't know if it's still the only one to have it built in, at least to the base library. So now we've got a good learning rate. How do we fine-tune the weights? So far we've just been running this fine-tune method without thinking much about what it's actually doing. But we did mention in chapter 1, lesson 1, briefly, basically what's happening with fine-tune. What is transfer learning doing? And before we look at that, let's take a question.
Is the learning rate plot in LR find plotted against one single mini batch?
No, it's not. It's actually just the standard kind of walking through the data loader. So just getting the usual mini batches of the shuffled data, and so it's kind of just normal training. And the only thing that's being different is that we're increasing the learning rate a little bit after each mini batch and keeping track of it.
Along with that, is the network reset to the initial status after each trial?
No, certainly not. We actually want to see how it learns. We want to see it improving. So we don't reset it to its initial state until we're done. So at the end of it, we go back to the random weights we started with, or whatever the weights were at the time we ran this. So what we're seeing here is something that's actually the actual learning that's happening as we at the same time increase the learning rate.
Why would an ideal learning rate found with a single mini batch at the start of training keep being a good learning rate even after several epochs and further loss reductions?
Great question. It absolutely wouldn't. So let's look at that too, shall we?
Yeah,
go on.
Can I ask one more?
Of course. No, this is an important point, so ask as many as you have.
This is very important. For the learning rate finder, why use the steepest and not the minimum?
We certainly don't want the minimum, because the minimum is the point at which it's not learning anymore, right? So this flat section at the bottom here means in this mini batch it didn't get better. So we want the steepest because that's the mini batch where it got the most improved. And that's what we want. We want the weights to be moving as fast as possible. As a rule of thumb, though, we do find that the minimum divided by 10 works pretty well. That's Sylvain's favorite approach, and he's generally pretty spot on with that. So that's why we actually print out those two things. LR min is actually the minimum divided by 10, and steepest point suggests the steepest point. Great. Good questions all. So remind ourselves what transfer learning does. So with transfer learning, remember what our neural network is. It's a bunch of linear models, basically, with activation functions between them. And our activation functions are generally ReLUs, rectified linear units. If any of this is fuzzy, have a look at the 04 notebook again to remind yourself. And so each of those linear layers has a bunch of parameters. So the whole neural network has a bunch of parameters. And so after we train a neural network on something like ImageNet, we have a whole bunch of parameters that aren't random anymore. They're actually useful for something. And we've also seen that the early layers seem to learn about fairly general ideas like gradients and edges, and the later layers learn about more sophisticated ideas like what do eyes look like, or what does fur look like, or what does text look like. So with transfer learning, we take a model, so in other words, a set of parameters, which has already been trained on something like ImageNet. We throw away the very last layer, because the very last layer is the bit that specifically says which one of those, in the case of ImageNet, 1000 categories, is this an image in. So we throw that away, and we replace it with random weights, sometimes with more than one layer of random weights, and then we train that. Now, yes.
Oh, I just wanted to make a comment, and that's that I think the learning rate finder, I think after you learn about it, the idea almost seems kind of so simple or approximate that it's like, wait, this shouldn't work, like, or, you know, shouldn't you have to do something more complicated or more precise? That it's like, I just want to highlight that this is a very surprising result, that some kind of such a simple approximate method would be so helpful.
Yeah, I would particularly say it's surprising to people who are not practitioners or who have not been practitioners for long. I've noticed that a lot of my students at USF have a tendency to kind of jump in to try to doing something very complex where they account for every possible imperfection from the start. And it's very rare that that's necessary. So one of the cool things about this is it's a good example of trying the easiest thing first and seeing how well it works.
And this was a very big innovation when it came out, that I think it's kind of easy to take for granted now, but this was super, super helpful when it was kind of a new.
It was super helpful, and it was also nearly entirely ignored. None of the research community cared about it, and it wasn't until FastAI, I think in our first course, talked about it that people started noticing. And we had quite a few years, in fact it's still a bit the case, where super fancy researchers still don't know about the learning rate finder, and get beaten by first lesson FastAI students on practical problems because they can pick learning rates better, and they can do it without a cluster of thousands of computers. Okay, so transfer learning. So we've got our pre-trained network, and so it's really important every time you hear the word pre-trained network, you're thinking a bunch of parameters which have particular numeric values and go with a particular architecture like ResNet 34. We've thrown away the final layer and replaced them with random numbers. And so now we want to train to fine-tune this set of parameters for a new set of images, in this case, pets. So fine-tune is the method we call to do that. And to see what it does, we can go learn.finetune ? And we can see the source code. And here is the signature of the function. And so the first thing that happens is we call freeze. So freeze is actually the method which makes it so only the last layer's weights will get stepped by the optimizer. So the gradients are calculated just for those last layers of parameters, and the step is done just for those last layer of parameters. So then we call fit, and we fit for some number of epochs, which by default is 1. We don't change that very often. And what that fit is doing is it's just fitting those randomly added weights, which makes sense, right? They're the ones that are going to need the most work, because at the time which we add them, they're doing nothing at all. They're just random. So that's why we spend 1 epoch trying to make them better. After you've done that, you now have a model which is much better than we started with. It's not random anymore. All the layers except the last are the same as the pre-trained network. The last layer has been tuned for this new data set. So the closer you get to the right answer, as you can kind of see in this picture, the smaller the steps you want to create. The smaller the steps you want to take, generally speaking. So the next thing we do is we divide our learning rate by 2, and then we unfreeze. So that means we make it so that all the parameters can now be stepped, and all of them will have gradients calculated. And then we fit for some more epochs, and this is something we have to the pass to the method. And so that's now going to train the whole network. So if we want to, we can kind of do this by hand, right? And actually CNN Learner will by default freeze the model for us, freeze the parameters for us. So we actually don't have to call freeze. So if we just create our learner and then fit for a while, this is 3 epochs of training just the last layer. And so then we can just manually do it ourselves, unfreeze. And so now at this point, as the question earlier suggested, maybe this is not the right learning rate anymore. So we can run lrfind again. And this time you don't see the same shape. You don't see this rapid drop because it's much harder to train a model that's already pretty good. But instead you just see a very gentle little gradient. So generally here, what we do is we kind of try to find the bit where it starts to get worse again and go about, which is about here, and go about 10, multiple of 10 less than that. So about 1e neg 5, I would guess, which, yep, that's what we picked. So then after unfreezing, finding our new learning rate, and then we can do a bunch more. And so here we are, we're getting down to 5.9% error, which is okay, but there's better we can do. And the reason we can do better is that at this point here, we're training the whole model at a 1e neg 5, so 10 to the minus 5 learning rate, which doesn't really make sense because we know that the last layer is still not that great. It's only had 3 epochs of training from random. So it probably needs more work. We know that the second last layer was probably pretty specialized to ImageNet and less specialized to pet breeds, so that probably needs a lot of work. Whereas the early layers, the kind of gradients and edges, probably don't need to be changed much at all. So what we'd really like is to have a small learning rate for the early layers and a bigger learning rate for the later layers. And this is something that we developed at FastAI, and we call it discriminative learning rates. And Jason Yasinski actually is a guy who wrote a great paper that some of these ideas are based on, which is he actually showed that different layers of the network really want to be trained at different rates, although he didn't kind of go as far as trying that out and seeing how it goes. It was more of a theoretical thing. So in FastAI, if we want to do that, we can pass to our learning rate, rather than just passing a single number, we can pass a slice. Now a slice is a special built-in feature of Python. It's just an object which basically can have a few different numbers in it. In this case, we're passing it 2 numbers. And the way we read those, basically what this means in FastAI as a learning rate is the very first layer will have this learning rate, 10 to the minus 6. The very last layer will be 10 to the minus 4. And the layers between the two will be kind of equal multiples. So they'll kind of be equally spaced learning rates from the start to the end. So here we can see basically doing our kind of own version of fine-tune. We create the learner, we fit with that automatically frozen version, we unfreeze, we fit some more. And so when we do that, you can see this works a lot better. We're getting down to 5.3, 5.1, 5.4% error. So that's pretty great. One thing we'll notice here is that we did kind of overshoot a bit. It seemed like more like epoch number 8 was better. So kind of back before, well, actually, let me explain something about fit one cycle. So fit one cycle is a bit different to just fit. So what fit one cycle does is it actually starts at a low learning rate. It increases it gradually for the first 1/3 or so of the batches until it gets to a high learning rate. The highest, this is why this is called LR max. It's the highest learning rate we get to. And then for the remaining 2/3 or so of the batches, it gradually decreases the learning rate. And the reason for that is just that, well, largely it's kind of like empirically, researchers have found that works the best. In fact, this was developed again by Leslie Smith, the same guy that did the learning rate finder. Again, it was a huge step, it really dramatically accelerated the speed at which we can train neural networks and also made them much more accurate. And again, the academic community basically ignored it. In fact, the key publication that developed this idea was not even did not even pass peer review. And so the reason I mention this now is to say that we don't really just want to go back and pick the model that was trained back here, because we could probably do better, because we really want to pick a model that's got a low learning rate. So what I would generally do here is I'd change this 12 to an 8, because this is looking good, and then I would retrain it from scratch. Normally I'd find a better result. You can plot the loss, and you can see how the training and validation loss moved along. And you can see here that the error rate was starting to get worse here. And what you'll often see is often the validation loss will get worse a bit before the error rate gets worse. We're not really seeing it so much in this case, but the error rate and the validation loss don't always, or they're not always kind of in lockstep. So what we're plotting here is the loss, but you actually kind of want to look to see mainly what's happening with the error rate, because that's actually the thing we care about. Remember, the loss is just like an approximation of what we care about that just happens to have a gradient that works out nicely. So how do you make it better now? We're already down to just 5.4, or if we'd stopped a bit earlier, maybe we could get down to 5.1 or less error on 37 categories. That's pretty remarkable. That's a very, very good pet breed predictor. If you want to do something even better, you could try creating a deeper architecture. So a deeper architecture is just literally putting more pairs of activation function, also known as a nonlinearity, followed by these little linear models, put more pairs onto the end. And basically the number of these sets of layers you have is the number that you'll see at the end of an architecture. So there's ResNet 18, ResNet 34, ResNet 50, so forth. Having said that, you can't really pick ResNet 19 or ResNet 38. I mean, you can make one, but nobody's created a pre-trained version of that for you. So you won't be able to do any fine tuning. So like you can theoretically create any number of layers you like, but in practice, most of the time you'll want to pick a model that has a pre-trained version. So you kind of have to select from the sizes people have pre-trained. And there's nothing special about these sizes. They're just ones that people happen to have picked out. For the bigger models, there's more parameters and more gradients that are going to be stored on your GPU, and you will get used to the idea of seeing this this error, unfortunately, out of memory. So that's not out of memory in your RAM, that's out of memory in your GPU. CUDA is referring to the language the system used for your GPU. So if that happens, unfortunately, you actually have to restart your notebook. So that's kernel, restart, and try again. And that's a really annoying thing, but such is life. One thing you can do if you get an out-of-memory error is after you'll see an nlearner call, add this magic incantation to FP16. What that does is it uses for most of the operations numbers that use half as many bits as usual, so they're less accurate. There's half precision floating point, or FP16. That will use less memory. And on pretty much any NVIDIA card created in 2020 or later, and some more expensive cards even created in 2019, that's often going to result in a 2 to 3 times speed up in terms of how long it takes as well. So here, if I add in to FP16, then I will be seeing often much faster training. And in this case, what I actually did is I switched to a ResNet 50, which would normally take about twice as long. And my per epoch time has gone from 25 seconds to 26 seconds. So the fact that we used a much bigger network and it was no slower is thanks to 2FP16. But you'll see our error rate hasn't improved. It's pretty similar to what it was. And so it's important to realize that just because we increase the number of layers, it doesn't always get better. So it tends to require a bit of experimentation to find what's going to work for you. And of course, don't forget, the trick is use small models for as long as possible to do all of your cleaning up and testing and so forth, and wait until you're all done to try some bigger models because they're going to take a lot longer.
A question,
okay,
Jeremy?
questions?
How do you know or suspect when you can, quote, do better?
You have to always assume you can do better because you never know. So you just have to, I mean, part of it though is, do you need to do better? So do you already have a good enough result to handle the actual task you're trying to do? Often people do spend too much time fiddling around with their models rather than actually trying to see whether it's already going to be super helpful. So as soon as you can actually try to use your model to do something practical, the better. But yeah, how much can you improve it? Who knows? I go through the techniques that we're teaching in this course and try them and see which ones help. And unless it's a problem that somebody has already tried before and written down their results in a paper or a Kaggle competition or something, there's no way to know how good can. So don't forget, after you do the questionnaire, to check out the further research section. And one of the things we've asked you to do here is to read a paper. So find the Learning Rate Finder paper and read it and see if you can kind of connect what you read up to the things that we've learned in this lesson, and see if you can maybe even implement your own Learning Rate Finder, as manually as you need to. See if you can get something that, based on reading the paper, you get to work yourself. You can even look at the source code of FastAI's Learning Rate Finder, of course. And then, can you make this classifier better? And so this is further research, right? So maybe you can start doing some reading to see what else could you do. Have a look on the forum, see what people are trying. Have a look on the book website or the course website to see what other people have achieved and what they did, and play around. So we've got some tools in our toolbox now for you to experiment with. So that is pet breeds. That is a pretty tricky computer vision classification problem, and we kind of have seen most of the pieces of what goes into the training of it. We haven't seen how to build the actual architecture, but other than that, we've kind of worked our way up to understanding what's going on. So let's build from there into another kind of data set, one that involves multi-label classification. So what's multi-label classification? Well, maybe let's look at an example. Here is a multi-label data set where you can see that it's not just one label on each image, but sometimes there's 3: bicycle, car, person. I don't actually see the car here, I guess it's being cropped out. So a multi-label data set is one where you still got one image per row, but you can have 0, 1, 2 or more labels per row. So we're going to have a think about and look at how we handle that. But first of all, let's take another question.
Does dropping floating point number precision, switching from FP32 to FP16, have an impact on final?
Yes, it does. Often it makes it better, believe it or not. It seems like, the kind of it's doing a little bit of rounding off is one way to think of it. Drop some of that precision, and so that creates a bit more bumpiness, a bit more uncertainty, a bit more of a stochastic nature. And when you introduce more slightly random stuff into training, it very often makes it a bit better. And so yeah, FP16 training often gives us a slightly better result, but I wouldn't say it's generally a big deal either way, and certainly it's not always better.
Would you say this is a bit of a pattern in deep learning? less exact and stochastic way.
For sure, not just in deep learning, but machine learning more generally. There's been some interesting research looking at like matrix factorization techniques, which if you want them to go super fast, you can use lots of machines, you can use randomization, and you often, when you then use the results, you often find you actually get better outcomes.
Just a brief plug for the Fast AI computational linear algebra course, which talks a little bit about random.
Does it really? Well, that sounds like a fascinating course. And look at that, it's #1 hit here on Google, so easy to find. Well, by somebody called Rachel Thomas. Hey, that's the person's got the same name as you, Rachel Thomas. All right. So how are we going to do multi-label classification? So let's look at a data set called Pascal, which is a pretty famous data set. We'll look at the version that goes back to 2007, been around for a long time. And it comes with a CSV file, which we will read in. CSV is comma-separated values. And let's take a look. Each row has a file name, one or more labels, and something telling you whether it's in the validation set or not. So the list of categories in each image is a space gene-limited string. It doesn't have a horse person, it has a horse and a person. PD here stands for pandas. Pandas is a really important library for any kind of data processing, and you'll use it all the time in machine learning and deep learning. So let's have a quick chat about it. Not a real panda, it's the name of a library, and it creates things called data frames. That's what the DF here stands for. And a data frame is a table containing rows and columns. Pandas can also do some slightly more sophisticated things than that, but we'll treat it that way for now. So you can read in a data frame by saying PD for pandas. Pandas read CSV, give it a file name. You've now got a data frame you can call head to see the first few rows of it, for instance. A data frame has a iloc, integer location, property, which you can index into as if it was an array. In fact, it looks just like NumPy. So colon means every row. Remember, it's row, comma, column. And 0 means 0th column. And so here is the first column of the data frame. You can do the exact opposite. So the 0th row and every column is going to give us the first row. And you can see the row has column headers and values. So it's a little bit different to NumPy. And remember, if there's a comma colon or a bunch of comma colons at the end of indexing in NumPy or PyTorch or Pandas, whatever, you can get rid of it. And these two are exactly the same. You could do the same thing here by grabbing the column by name. The first column is fname, so you can say df fname to get that first column. You can create new columns. So here's a tiny little data frame I've created from a dictionary. And I could create a new column by, for example, adding 2 columns. And you can see there it is. So it's like a lot like NumPy or PyTorch, except you have this idea of kind of rows and column named columns, and so it's all about this kind of tabular data. I find its API pretty unintuitive. A lot of people do, but it's fast and powerful. So it takes a while to get familiar with it, but it's worth taking a while. And the creator of Pandas wrote a fantastic book called Python for Data Analysis, which I've read both versions and I found it fantastic. It doesn't just cover pandas, it covers other stuff as well, like IPython and NumPy and Matplotlib. So highly recommend this book. This is our table. So what we want to do now is construct data loaders that we can train with. And we've talked about the data block API as being a great way to create data loaders. So let's use this as an opportunity to create a data loaders for a create a data block and then data loaders for this. And let's try to do it like right from square one. So let's see exactly what's going on with a data block. So first of all, let's remind ourselves about what a data set and a data loader is. A data set is an abstract idea of a class. You can create a data set. A data set is anything which you can index into it, like so, and you can take the length of it. like so. So for example, the list of the lowercase letters along with a number saying which lowercase letter it is, I can index into it to get 0, A. I can get the length of it to get 26. And so therefore this qualifies as a data set. And in particular, data sets, normally you would expect that when you index into it, you would get back a tuple because you've got the independent and dependent variables. Not necessarily always just two things. There could be more, there could be less, but two is the most common. So once we have a data set, we can pass it to a data loader. We can request a particular batch size. We can shuffle or not. And so there's our data loader from A. We could grab the first value from that iterator. And here is the shuffled 7 is H, 4 is E, 20 is U, and so forth. And so I remember a mini batch has a mini batch of the independent variable and a mini batch of the dependent variable. If you want to see how the two correspond to each other, you can use zip. So if I zip passing in this list and then this list, so B0 and B1, you can see what zip does in Python is it grabs one element from each of those in turn and gives you back the tuples of the corresponding elements. Since we're just passing in all of the elements of B to this function, Python has a convenient shortcut for that, which is just say star B. And so star means insert into this parameter list each element of B, just like we did here. So these are the same thing. So this is a very handy idiom that we use a lot in Python. Zip star something is kind of a way of like transposing something from one orientation to another. All right, so we've got a data set, we've got a data loader. And then what about data sets? Well, data sets is an object which has a training data set and a validation set data set. So let's look at one. So normally you don't start with kind of an enumeration like this, like with an independent variable and a dependent variable. Normally you start with like a file name, for example. And then you kind of calculate or compute or transform your file name into an image by opening it, and a label by, for example, looking at the file name and grabbing something out of it. So for example, we could do something similar here. This is what datasets does. So we could start with just the lowercase letters. So this is still a dataset, right? Because we can index into it and we can get the length of it, although it's not giving us tuples yet. So if we now pass that list to the datasets class and index into it, we get back a tuple. And it's actually a tuple with just one item. This is how Python shows a tuple with one item, is it puts it in parentheses and a comma and then nothing. Okay. So in practice, what we'd really want to do is to say like, okay, we'll take this and do something to compute an independent variable and do something to compute a dependent variable. So here's a function we could use to compute an independent variable, which is to stick an A on the end, and our dependent variable might just be the same thing with a B on the end. So here's two functions. So for example, now we can call datasets, passing in A, and then we can pass in a list of transformations to do. And so in this case, I've just got one, which is this function, add an A on the end. So now if I index into it, I don't get A anymore, I get AA. If you pass multiple functions, then it's going to do multiple things. So here I've got F1, then F2, AAB. Adds this one, then adds this one. And you'll see this is a list of lists, and the reason for that is that you can also pass something like this, a list containing F1, a list containing F2, and this will actually take each element of A, pass it through this list of functions, and there's just one of them to give you AA, and then start again and separately pass it through this list of functions, there's just one, to get AB. And so this is actually kind of the main way we build up independent variables and dependent variables in FastAI, is we start with something like a file name and we pass it through two lists of functions. One of them will generally kind of open up the image, for example, and the other one will kind of parse the file name. for example, and give you a independent variable and a dependent variable. So you can then create a data loaders object from datasets by passing in the datasets and a batch size. And so here you can see I've got shuffled OA, IA, etc., OB, IB, etc. So this is worth studying to make sure you understand what datasets and data loaders are. We don't often have to create them from scratch. We can create a data block to do it for us. But now we can see what the data block has to do. So let's see how it does it. So we can start by creating an empty data block. So an empty data block is going to take our data frame. So we're going to go back to looking at our data frame, which remember was this guy. And so if we pass in our data frame, we'll now find that this data block has created data sets, a training and a validation data set for us. And if we look at the training set, it'll give us back an independent variable and a dependent variable, and we'll see that they are both the same thing. So this is the first row of the table that's actually shuffled. So it's a random row of the table repeated twice. And the reason for that is by default, the data block assumes that we have two things, the independent variable and the dependent, or the input and the target. And by default, it just copies. It just keeps exactly whatever you gave it. To create the training set and the validation set, by default, it just randomly splits the data with a 20% validation set. So that's what's happened here. So this is not much use. What we actually want to do, if we look at X, for example, is grab the F name, the file name field, because we want to open this image. That's going to be our independent variable. And then for the label, we're going to want this here, person cat. So we can actually pass these as parameters. Get X and get Y are functions that return the bit of data that we want. And so you can create and use a function in the same line of code in Python by saying lambda. So lambda r means create a function, doesn't have a name, it's going to take a parameter called r. We don't even have to say return. It's going to return the fname column in this case. And get y is something which is a function that takes an r and returns the labels column. So now we can do the same thing called dblock.datasets. We can grab a row from that, from the training set, and you can see, look, here it is. There is the image file name, and there is the space delimited list of labels. So here's exactly the same thing again, but done with functions. Okay, so now the one line of code above has become 3 lines of code, but it does exactly the same thing. Okay. We don't get back the same result because the training set, well, wait, why don't we get the same result? Oh, I know why. Because it's randomly it's randomly picking a different validation set because the random split is done differently each time. So that's why we don't get the same result. One thing to note, be careful of lambdas. If you want to save this data block for use later, you won't be able to. Python doesn't like saving things that contain lambdas. So most of the time in the book and the course, we normally use avoid lambdas for that reason, because it's often very convenient to be able to save things. We use the word here serialization. That just means, basically it means saving something. This is not enough to open an image because we don't have the path. So to turn this into, so rather than just using this function to grab the fname column, we should actually use pathlib to go path/train and then column. And then for the y, again, the labels is not quite enough. We actually have to split on space. But this is Python. We can use any function we like. And so then we use the same 3 lines of code as here. And now we've got a path and a list of labels. So that's looking good. So we want this path to be opened as an image. So the data block API lets you pass a blocks argument where you tell it for each of the things in your tuple, so there's 2 of them, what kind of block do you need? So we need an image block to open an image. And then in the past, we've used a category block for categorical variables, but this time we don't have a single category, we've got multiple categories. So we have to use a multi-category block. So once we do that and have a look, we now have a 500 by 375 image as our independent variable. And as a dependent variable, we have a long lists of zeros and ones. The long list of zeros and ones is the labels as a one-hot encoded vector, a rank 1 tensor. And specifically, there will be a 0 in every location where, in the vocab, where there is not that kind of object in this image, and a 1 in every location where there is. So for this one, there's just a person. So this must be the location in the vocab where there's a person. Do you have any questions? So one-hot encoding is a very important concept, and we didn't have to use it before, right? We could just have a single integer saying which one thing is it. But when we've got lots of things, lots of potential labels, it's convenient to use this one-hot encoding. And it's kind of what it's actually what's going to happen with the actual matrices anyway. When we actually compare the activations of our neural network to the target, it's actually going to be comparing each one of these. Okay, so the categories, as I mentioned, is based on the vocab. So we can grab the vocab from our dataset subject, and then we can say, okay, let's look at the first row, and let's look at the dependent variable, and let's look for where the dependent variable is 1. Okay, and then we can have a look past those indexes to the vocab and get back a list of what it actually was there. And again, each time I run this, I'm going to get different results. So each time we run this, we're going to get different results because I called .datasets again here. So it's going to give me a different train test split. And so this time it turns out that this is actually a chair. And we have a question.
Shouldn't the tensor be of integers? Why is it a tensor of floats?
Yeah, conceptually this is a tensor of integers. They can only be 0 or 1. But we're going to be using a cross-entropy style loss function. So we're going to actually need to do floating point calculations on them. That's going to be faster to just store them as float in the first place rather than converting backwards and forwards. Even though they're conceptually an int, we're not going to be doing kind of int style calculations with them. Good question. I mentioned that by default, the data block uses a random split. You might have noticed in the data frame, though, it said here's a column saying what validation set to use. And if the data set you're given tells you what validation set to use, you should generally use it because that way you can compare your validation set results to somebody else's. So you can pass a splitter argument, which again is a function. And so we're going to pass it a function that's also called splitter. And the function is going to return the indexes where it's not valid. And that's going to be the training set. And the indexes where it is valid, that's going to be the validation set. And so the splitter argument is expected to return 2 lists of integers. And so if we do that, we get again the same thing, but now we're using the correct train and validation sets.
Another question?
Sure.
Any particular reason we don't use floating point 8? Is it just that the precision's too low?
Yeah, trying to train with 8-bit precision is super difficult because it's It's so flat and bumpy, it's pretty difficult to get decent gradients. But it's an area of research. The main thing people do with 8-bit or even 1-bit data types is they take a model that's already been trained with 16-bit or 32-bit floating point, and then they kind of round it off. It's called discretizing, to create a kind of purely integer or even binary network, which can do inference much faster. Figuring out how to train with such low precision data is an area of active research. I suspect it's possible, and I mean, people have fiddled around it and had some success. I think it could turn out to be super interesting, particularly for stuff that's been done on like low-powered devices that might not even have a floating point unit. Right, so the last thing we need to do is to add our item transforms, random resize crop. We've talked about that enough, so I won't go into it, but basically that means we now are going to ensure that everything has the same shape so that we can collate it into a data loader. So now, rather than going .datasets, go .dataloaders and display our data. And remember, if something goes wrong, as we saw last week, you can call summary to find out exactly what's happening in your data block. So now, this is something really worth studying, this section, because data blocks are super handy. And if you haven't used FastAI 2 before, they won't be familiar to you because no other library uses them. And so like this has really shown you how to go right back to the start and gradually build them up. So hopefully that'll make a whole lot of sense now. Now we're going to need a loss function again. And to do that, let's start by just creating a learner. Let's create a ResNet 18 from the data loaders object that we just created. And let's grab one batch of data, and then let's put that into our mini batch of independent variables. And then learn.model is the thing that actually contains the model itself, in this case a CNN. And you can treat it as a function. And so therefore we can just pass something to it. And so if we pass a mini batch of the independent variable to learn.model, it will return the activations from the final layer. And that is shape 64 by 20. So anytime you get a tensor back, look at its shape. And in fact, before you look at its shape, predict what the shape should be. And then make sure that you're right. If you're not, either you guessed wrong, so try to understand where you made a mistake, or there's a problem with your code. In this case, 64 by 20 makes sense because we have a mini batch size of 64. And for each of those, we're going to make predictions about what probability is each of these 20 possible categories. We have a question.
Two questions.
Two questions, all right.
Is the data block API compatible with out-of-core data sets like Dask?
Yeah, the data block API can do anything you want it to do. So you're passing it, if we go back to the start. So you can create an empty one, and then you can pass it anything that is indexable. And yeah, so that can be anything you like. And pretty much anything can be made indexable in Python, and something like Dask is certainly indexable. So that works perfectly fine. If it's not indexable, like it's a network stream or something like that, then the data loaders data sets APIs directly, which we'll learn about either in this course or the next one. But yeah, anything that you can index into, which certainly includes Dask, you can use with data blocks.
Next question. Where do you put images for multi-label with that CSV table? Should they be in the same directory?
They can be anywhere you like. So in this case, we used a pathlib object like so. And in this case, by default, it's going to be using, let's think about this. So what's happening here is the path is, oh, it's saying dot. Okay, the reason for that is that path.basePath is currently set to path, and so that displays things relative. So let's get rid of that. Okay, so the path we set is here, right? And so then when we said get x, it's saying path/chain/whatever, right? So this is an absolute path. And so here is the exact path. So you can put them anywhere you like, you just have to say what the path is. And then if you want to not get confused by having this big long prefix that we don't want to see all the time, just set base path to the path you want everything to be relative to, and then it'll just print things out in this more convenient manner. Right, so this is really important that you can do this, that you can create a learner, that you can grab a batch of data, that you can pass it to the model. This is just plain PyTorch, this line here, right? No fast AI. You can see the shape, right? You can recognize why it has this shape. And so now if you have a look, here are the 20 activations. Now, this is not a trained model. It's a pre-trained model with a random set of final layer weights. So these specific numbers don't mean anything, right? But it's just worth remembering this is what activations look like. And most importantly, they're not between 0 and 1. And if you remember from the MNIST notebook, we know how to scale things between 0 and 1. We can pop them into the sigmoid function. So the sigmoid function is something that scales everything to be between 0 and 1. So let's use that. You'll also hopefully remember from the MNIST notebook that the MNIST loss function first did sigmoid, and then it did torch.where. And then it did .mean. So we're going to use exactly the same thing as the MNIST loss function, and we're just going to do one thing, which is going to add .log for the same reason that we talked about when we were looking at softmax. We talked about why log is a good idea as a transformation. We saw in the MNIST notebook we didn't need it, but we're going to train faster and more accurately if we use it, because it's just more, it's going to be better behaved, as we've seen. So this particular function, which is identical to MNIST loss plus .log, has a specific name, and it's called binary cross entropy. And we used it for the 3s versus 7s problem to decide whether that column is it a 3 or not. But because we can use broadcasting in PyTorch and element-wise arithmetic, this function, when we pass it a whole matrix, is going to be applied to every column. So is the first column, so it'll basically do a torch.where on every column separately and every item separately. So that's great. It basically means that this binary cross entropy function is going to be just like MNIST loss, but rather than just being, is this a number 3, it'll be, is this a dog? Is this a cat? Is this a car? Is this a person? Is this a bicycle? And so forth. So this is where it's so cool in PyTorch. We can kind of write one thing and then kind of have it expand to handle higher dimensional tensors without doing any extra work. We don't have to write this ourselves, of course, because PyTorch has one, and it's called f.binary cross entropy. So we can just use PyTorches. As we've talked about, there's always a equivalent module version. So this is exactly the same thing as a module, nn.bce loss. These ones don't include the initial sigmoid, actually. If you want to include this initial sigmoid, you need f.binary cross entropy with logits, or the equivalent nn.bce with logits loss. So BCE is binary cross entropy. And so those are 2 functions plus 2 equivalent classes for multi-label or binary problems. And then the equivalent for single label, like MNIST and PETS, is NLL loss and cross entropy. So that's the equivalent of binary cross entropy and binary cross entropy with logits. So these are pretty awful names. I think we can all agree. But it is what it is. So in our case, we have a one hot encoded target, and we want the one with the sigmoid in. So the equivalent built in is called BCE with logits loss. So that we can make that our loss function. We can compare the activations to our targets, and we can get back a loss. And then that's what we can use to train. And then finally, before we take our break, we also need a metric. Now previously we've been using as a metric accuracy, or actually error rate. Error rate is 1 minus accuracy. Accuracy only works for single label data sets like MNIST and PETS. Because what it does is it takes the input, which is the final layer activations, and it does argmax. What argmax does is it says, what is the index of the largest number in those activations? So for example, for MNIST, maybe the highest probability is 7. So this argmax would return 7. And then it says, okay, those are my predictions. And then it says, okay, is the prediction equal to the target or not? And then take the floating point mean. So that's what accuracy is. So argmax only makes sense when there's a single maximum thing you're looking for. In this case, we've got multi-label. So instead, we have to compare each activation to some threshold. By default, it's 0.5. And so we basically say if the sigmoid of the activation is greater than 0.5, let's assume that means that category is there. And if it's not, let's assume it means it's not there. And so this is going to give us a list of trues and falses for the ones that based on the activations it thinks are there. And we can compare that to the target. And then again, take the floating point mean. So we can use the default threshold of 0.5. But we don't necessarily want to use 0.5. We might want to use a different threshold. And remember, we have to pass, when we create our learner, we have to pass to the metrics argument, a function. So what if we want to use a threshold other than 0.5? Well, we'd like to create a special function, which is accuracy multi with some different threshold. And the way we do that is we use a special built-in Python called partial. Let me show you how partial works. Here's a function called say hello. Say hello to somebody with something. So say hello Jeremy, well the default is hello. So it says hello Jeremy. Say hello Jeremy, comma ahoy. It's going to be ahoy Jeremy. Let's create a special version of this function that will be more suitable for Sylvain. It's going to use French. So we can say partial, create a new function that's based on the say hello function, but it's always going to set say what to bonjour. And we'll call that F. So now F Jeremy is bonjour Jeremy, and F Sylvain is bonjour Sylvain. So you see we've created a new function from an existing function by fixing one of its parameters. So we can do the same thing for accuracy multi. Say let's use a threshold of 0.2, and we can pass that to metrics. And so let's create a CNN learner. And you'll notice here we don't actually pass a loss function. And that's because FastAI is smart enough to realize, hey, you're doing a classification model with a multi-label dependent variable. So I know what loss function you probably want. So it does it for us. So we can call fine tune. And here we have an accuracy of 94.5 after the first few, and eventually 95.1. That's pretty good. We've got an accuracy of over 95%. Was 0.2 a good threshold to pick? Who knows? Let's try 0.1. Oh, that's a worse accuracy. So I guess in this case, we could try a higher threshold, 94. Also not good. So what's the best threshold? Well, what we could do is call getPreds to get all of the predictions and all of the targets. And then we could calculate the accuracy at some threshold. And then we could say, okay, let's grab lots of numbers between 0.05 and 0.95. and you, with the list comprehension, calculate the accuracy for all of those different thresholds and plot them. Looks like we want a threshold somewhere a bit above 0.5. So cool, we can just use that, and it's going to give us 96 and a bit, which is going to give us a better accuracy. This is a something that a lot of theoreticians would be uncomfortable about. I've used the validation set to pick a hyperparameter, a threshold, right? And so people might be like, oh, you're overfitting using the validation set to pick a hyperparameter. But if you think about it, this is a very smooth curve, right? It's not some bumpy thing where we've accidentally kind of randomly grabbed some unexpectedly good value. When you're picking a single number from a smooth curve, this is where the theory of like, don't use a validation set for hyperparameter tuning doesn't really apply. So it's always good to be practical, right? Don't treat these things as rules, but as rules of thumb. Okay, so let's take a break for 5 minutes, and we'll see you back here in 5 minutes' time. Right, welcome back. So I want to show you something really cool. Image regression. So we are not going to learn how to use a FastAI image regression application because we don't need one. Now that we know how to build stuff up with loss functions and the data block API ourselves, we can invent our own applications. So there is no image regression application per se, but we can do image regression really easily. What do we mean by image regression? Well, remember back to lesson, I think it was lesson 1, we talked about the 2 basic types of machine learning, or supervised machine learning. Regression and classification. Classification is when our dependent variable is a discrete category or set of categories. And regression is when our dependent variable is a continuous number, like an age or XY coordinate or something like that. So image regression means our independent variable is an image and our dependent variable is a one or more continuous values. And so here's what that can look like, which is the BWE head pose data set. It has a number of things in it, but one of the things we can do is find the midpoint of a person's face. See. So the BWE head pose data set. So the BWE head pose data set comes from this paper, Random Forest Real-Time 3D Face Analysis. So thank you to those authors. We can grab it in the usual way, untar data, and we can have a look at what's in there. And we can see there's 24 directories numbered from 1 to 24. There's 1, 2, 3, and each one also has a .obj file. We're not going to be using the .obj file, just the directories. So let's look at one of the directories. And as you can see, there's 1,000 things in the first directory. So each one of these 24 directories is one different person that they photographed. And you can see for each person, there's frame 3 pose, frame 3 RGB, frame 4 pose, frame 4 RGB, and so forth. So in each case, we've got the image, which is the RGB, and we've got the pose, which is the pose.txt. So as we've seen, we can use get image files to get a list of all of the image files recursively in a path. And so once we have an image file name, like this one, we can turn it into a pose file name by removing the last 1, 2, 3, 4, 5, 6, 7 letters and adding back on pose.txt. And so here is a function that does that. And so you can see I can pass in an image file to image to pose and get back a pose file. Right, so PIL image.create is the FastAI way to create an image, at least a PIL image. It has a shape. In computer vision, they're normally backwards. They normally do columns by rows. So that's why it's this way around, whereas PyTorch and NumPy tensors and arrays are rows by columns. So that's confusing, but that's just how things are, I'm afraid. So here's an example of an image. When you look at the README from the dataset website, they tell you how to get the center point from one of the text files, and it's just this function, so it doesn't matter. It is what it is. We call it get center, and it will return the XY coordinate of the center of the person's head, face. So we can pass this as get Y, because get Y, remember, is the thing that gives us back the label. Okay. So here's the thing, right? We can create a data block, and we can pass in as the independent variables block, image block as usual. And then the dependent variables block, we can say point block, which is a tensor with 2 values in. And now by combining these two things, this says we want to do image regression with a dependent variable with 2 continuous values. To get the items, you call get image files. To get the Y, we'll call the get center function. To split it, so this is important, we should make sure that the validation set contains one or more people that don't appear in the training set. So I'm just going to grab person number 13, just grabbed it randomly, and I'll use all of those images as the validation set. Because I think they did this with a Xbox Connect, video thing. So there's a lot of images that look almost identical. So if you randomly assigned them, then you would be massively overestimating how effective you are. You want to make sure that you're actually doing a good job with a random, with a new set of people, not just a new set of frames. That's why we use this. And so func splitter is a splitter that takes a function, and in this case we're using lambda to create the function. We will use data augmentation, and we will also normalize. So this is actually done automatically now, but in this case we're doing it manually. So this is going to subtract the mean and divide by the standard deviation of the original data set that the pre-trained model used, which is ImageNet. So that's our data block. And so we can call data loaders to get our data loaders, passing in the path and show batch, and we can see that looks good, right? Here's our faces and the points. And so let's, particularly for as a student, don't just look at the pictures, look at the actual data. So grab a batch, put it into an XB and a YB, X batch and Y batch, and have a look at the shapes. And make sure they make sense. So why is this 64 by 1 by 2? So it's 64 in the mini batch, 64 rows. And then the coordinates is a 1 by 2 tensor. So there's a single point with 2 things in it. Because you could have hands, face, and armpits or whatever, or nose and ears and mouth. So in this case, we're just using 1 point, and the point is represented by 2 values, the X and the Y. And then why is this 64 by 3 by 240 by 320? Well, there's 240 rows by 320 columns. That's the pixels. That's the size of the images that we're using. Mini batch is 64 items. And what's the 3? The 3 is the number of channels, which in this case means the number of colors. If we open up some random grizzly bear image, and then we go through each of the elements of the first axis and do a show image, you can see that it's got the red, the green, and the blue as the 3 channels. So that's how we store a 3-channel image. Is it stored as a 3 by number of rows by number of columns rank 3 tensor. And so a mini batch of those is a rank 4 tensor. So that's why this is that shape. So here's a row from the dependent variable. Okay, and there's that XY location we talked about. So we can now go ahead and create a learner, passing in our data loaders as usual, passing in a pre-trained architecture as usual. And if you think back, you may just remember in lesson 1, we learned about Y-range. Y-range is where we tell FastAI what range of data we expect to see in the dependent variable. And so we want to use this generally when we're doing regression. So the range of our coordinates is between -1 and 1. That's how FastAI and PyTorch treats coordinates. The left-hand side is -1, or the top is -1, and the bottom and the right are 1. So there's no point predicting something that's smaller than -1 or bigger than 1, because that is not in the area that we use for our coordinates.
I have a question.
Sure, just a moment. So how does Y-range work? Well, it actually uses this function called sigmoid range, which takes the sigmoid of x, multiplies by high minus low, and adds low. And here is what sigmoid range looks like for -1 to 1. It's just a sigmoid where the bottom is the low and the top is the high. And so that way, all of our activations are going to be mapped to the range from -1 to 1. Yes, Rachel?
Can you provide images with an arbitrary number of channels as inputs, specifically more than 3 channels?
Yeah, you can have as many channels as you like. We've certainly seen images with less than 3, because we've been grayscale. More than 3 is common as well. You could have like an infrared band, or like satellite images often have multispectral. There's some kinds of medical images where there are bands that are kind of outside the visible range. Your pre-trained model will generally have 3 channels. So FastAI does some tricks to use 3-channel pre-trained models for non-3-channel data. But that's the only tricky bit. Other than that, it's just it's just an axis that happens to have 4 things or 2 things or 1 thing instead of 3 things. There's nothing special about it. Okay, we didn't specify a loss function here, so we get whatever it gave us, which is a MSE loss. So MSE loss is mean squared error, and that makes perfect sense, right? You would expect mean squared error to be a reasonable thing to use for regression. We're just testing how close we are to the target, and then taking the square, taking the mean. We didn't specify any metrics, and that's because mean squared error is already a good metric. Like it has nice gradients, it behaves well, and it's also the thing that we care about. So we don't need a separate metric to track. So let's go ahead and use LR_find, and we can pick a learning rate, so maybe about 10 to the -2. We can call fine tune, and we get a valid loss of 0.0001, and so that's the mean squared error, so we should take the square root. So on average, we're about 0.01 off in a coordinate space that goes between -1 and 1. So that sounds super accurate. Took about 3 and a bit minutes to run. So we can always call in FastAI, and we always should, show results. See what our results look like. And as you can see, FastAI has automatically figured out how to display the combination of an image independent variable and a point dependent variable. On the left is the target, and on the right is the prediction. And as you can see, it is pretty close to perfect. You know, one of the really interesting things here is we used fine tune, even although, think about it, the thing we're fine tuning, ImageNet, isn't even an image regression model. So we're actually fine tuning an image classification model to become something totally different, an image regression model. Why does that work so well? Well, because an ImageNet classification model must have learnt a lot about kind of how images look, what things look like, and where the pieces of them are, to kind of know how to figure out what breed of animal something is, even if it's partly obscured by a bush, or it's in the shade, or it's turned in different angles. You know, these pre-trained image models are incredibly powerful computers, you know, computing algorithms. So built into every ImageNet pre-trained model is all this capability that it had to learn for itself. So asking it to use that capability to figure out where something is just actually not that hard for it. And so that's why we can actually fine-tune an ImageNet classification model to create something completely different, which is a point image regression model. So I find that incredibly cool, I gotta say. So again, look at the further research after you've done the questionnaire. And particularly if you haven't used data frames before, please play with them because we're going to be using them more and more.
A question.
I'll just do the last one. And also go back and look at the bear classifier from Notebook 2 or whatever. Hopefully you created some other classifier for your own data. Because remember we talked about how it would be better if the bear classifier could also recognize that there's no bear at all. Or maybe there's both a grizzly bear and a black bear, or a grizzly bear and a teddy bear. So if you retrain it using multi-label classification, see what happens. See how well it works when there's no bears. And see whether it changes the accuracy of the single label model when you turn it into a multi-label problem. So have a fiddle around and tell us on the forum what you find. And we've got a question, Rachel.
Is there a tutorial showing how to use pre-trained models on 4-channel images? Also, how can you add a channel to a normal image?
What was the last bit? How do you add a channel to an image? I don't know what that means. Like how, like, I don't know. You can't, like an image is an image. You can't add a channel to an image, is what it is. I don't know if there's a tutorial, but we can certainly make sure somebody on the forum has shown how to do it. It's super straightforward. It should be pretty much automatic. Okay. We're going to talk about collaborative filtering. What is collaborative filtering? Well, think about on Netflix or whatever. You might have watched a lot of movies that are sci-fi and have a lot of action and were made in the 70s. And Netflix might not know anything about the properties of movies you watched. It might just know that they're movies with titles and IDs. But what it could absolutely see without any manual work is find other people that watched the same movies that you watched. And it could see what other movies those people watched that you haven't. And it would probably find you would probably find they're also science fiction and full of action and made in the 70s. So we can use an approach where we recommend things, even if we don't know anything about what those things are, as long as we know who else has used or recommended things that are similar, the same kind, many of the same things that you've liked or used. This doesn't necessarily mean users and products. In fact, in collaborative filtering, instead of saying products, we normally say items. And items could be links you click on, diagnoses for a patient, and so forth. So there's a key idea here, which is that in the underlying items, and we're going to be using movies in this example, there are some features. They may not be labeled, but there's some underlying concept of features of those movies, like the fact that there's a action concept and a sci-fi concept and a 1970s concept. Now, you were never actually told Netflix you like these kinds of movies, and maybe Netflix never actually added columns to their movies saying what movies are those types. But as long as, in the real world, there's this concept of sci-fi and action and movie age, and that those concepts are relevant for at least some people's movie watching decisions. As long as this is true, then we can actually uncover these, they're called latent factors, these things that kind of decide what kind of movies you want to watch. And they're latent because nobody necessarily ever wrote them down or labeled them or communicated them in any way. So let me show you what this looks like. So there's a great data set we can use called Movie Lens, which contains tens of millions of movie rankings. And so a movie ranking looks like this. It has a user number, a movie number, a rating, and a timestamp. So we don't know anything about who user number 196 is. I don't know if that is Rachel or Sylvain or somebody else. I don't know what movie number 242 is. I don't know if that's Casablanca or Lord of the Rings or The Mask. And then rating is a number between, I think it was 1 and 5.
A question.
Sure.
In traditional machine learning, we perform cross-validations and k-fold training to check for variance and bias trade-off. Is this common in training deep learning models as well?
So cross-validation is a technique where you don't just split your data set into one training set and one validation set, but you basically do it 5 or so times, like 5 training sets and like 5 validation sets representing different overlapping subsets. And basically this used to be done a lot because people often used to have not enough data to get a good result. And so this way, rather than kind of having 20% that you would leave out each time, you could just leave out like 10% each time. Nowadays, it's less common that we have so little data that we need to worry about the complexity and extra time of lots of models. It's done on Kaggle a lot. Because on Kaggle, every little fraction of a percent matters. But it's not a deep learning thing or a machine learning thing or whatever. It's just a, lots of data or not very much data thing. And do you care about the last decimal place of them or not? It's not something we're going to talk about, certainly in this part of the course, if ever, because it's not something that comes up in practice that often as being that important.
There are 2 more questions. What would be some good applications of collaborative filtering outside of recommender systems?
Well, I mean, depends how you define recommender system. If you're trying to figure out what kind of other diagnoses might be applicable to a patient, I guess that's kind of a recommender system. Or you're trying to figure out where somebody is going to click next or whatever, it's kind of a recommender system. But, really conceptually, it's anything where you're trying to learn from past behavior, where that behavior is kind of like a thing happened to an entity.
What is an approach to training using video streams, i.e. from drone footage instead of images? Would you need to break up the footage into image frames?
In practice, quite often you would, because images just tend to be pretty big. Sorry, videos tend to be pretty big. There's a lot of things.
So, I mean, theoretically, the time could be the 4th channel.
Yeah, or a 5th channel. So,
5th channel.
I mean, if it's a full color movie, you can absolutely have, well, I guess 4th, because you can have, it would be a rank 5 tensor being batch by time, by color, by row, by column. But often that's too computationally and too memory intensive. So sometimes people just look at one frame at a time. Sometimes people use a few frames around kind of the key frame, like 3 or 5 frames at a time. And sometimes people use something called a recurrent neural network, which we'll be seeing in the next week or 2. It's treated as a sequence data. Yeah, there's all kinds of tricks you can do to try and work with that. Conceptually, though, there's no reason you can't just add an additional axis to your tensors and everything just work. It's just a practical issue around time and memory.
And someone else noted that it's pretty fitting that you mentioned the movie The Mask.
Yes, it was not an accident because I've got masks on the brain. I'm not sure if we're allowed to like that movie anymore, though. I kind of liked it when it came out. I don't know what I'd think nowadays. It's a while. Okay, so let's take a look. So we can untar data ML100K. So ML100K is a small subset of the full set. There's another one that we can grab, which has got the whole lot, 25 million. But 100K is good enough for messing around. So if you look at the README, you'll find the main table. The main table is in a file called u.data. So let's open it up with read.csv again. This one is actually not comma separated values, it's tab separated. Rather confusingly, we still use CSV and just say delimiter is a tab, \t is tab. There's no row at the top saying what the columns are called. So we say header is none and then pass in a list of what the columns are called. .head will give us the first 5 rows, and we mentioned just before what it looks like. It's not a particularly friendly way to look at it. So what I'm going to do is I'm going to cross tab it. And so what I've done here is I've grabbed the top, I can't remember how many it was. Well, okay, 1, 2, 3, 4, 15 or 20 movies based on the most popular movies and the top bunch of users who watch the most movies. And so I've basically kind of reoriented this. So for each user, I have all the movies they've watched and the rating they gave them. So empty spots represent users that have not seen that movie. So this is just another way of looking at this same data. So basically what we want to do is guess what movies we should tell people they might want to watch. And so it's basically filling in these gaps to tell user 212, do you think they might like movie 49 or 79 or 99 best to watch next? So let's assume that we actually had columns for every movie that represented, say, how much sci-fi they are, how much action they are, and how old they are. And maybe they're between -1 and 1. And so like the Last Skywalker is very sci-fi, fairly action, and definitely not old. And then we could do the same thing for users. So we could say user 1 really likes sci-fi, quite likes action, and really doesn't like old. And so now if you multiply those together, and remember in PyTorch and NumPy, you have element-wise calculations. So this is going to multiply each corresponding item. It's not matrix multiplication. If you're a mathematician, don't go there. This is element-wise multiplication. If we want matrix multiplication, it would be an @ sign. So if we multiply each element together next with the equivalent element in the other one, and then sum them up, that's going to give us a number which will basically tell us how much do these two correspond. Because remember, two negatives multiply together to get a positive. So user 1 likes exactly the kind of stuff that the Last Skywalker has in it, and so we get 2.1. Multiplying things together element-wise and adding them up is called the dot product. Okay, and we use it a lot, and it's the basis of matrix, I didn't say modification, matrix multiplication. Multiplication. So make sure you know what a dot product is. It's this. So Casablanca is not at all sci-fi, not much action, and is certainly old. So if we do user 1 times Casablanca, we get a negative number. So we might think, okay, user 1 won't like this movie. Problem is, we don't know what the latent factors are, And even if we did, we don't know how to label a particular user or a particular movie with them. So we have to learn them. How do we learn them? Well, we can actually look at a spreadsheet. So I've got a spreadsheet version. So we have a spreadsheet version, which is basically what I did was I popped this table into Excel, and then I randomly created a, let's count this now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I randomly created a 15 by 5 table here. So these are just random numbers. And I randomly created a 5 by 15 table here. And I basically said, okay, well, let's just pretend, let's just assume that every movie and every user has 5 latent factors. I don't know what they are. And let's then do a matrix multiply of this set of factors by this set of factors. And a matrix multiply of a row by a column is identical to a dot product of 2 vectors. So that's why I can just use matrix multiply. So this is just what this first cell contains. So they then copied it to the whole thing. So all these numbers there are being calculated from the row latent factors dot product with, or matrix multiply with, the column latent factors. So in other words, I'm doing exactly this calculation, but I'm doing them with random numbers. And so that gives us a whole bunch of values, right? And then what I could do is I could calculate a loss by comparing every one of these numbers here to every one of these numbers here, and then I could do mean squared error. And then I could use stochastic gradient descent to find the best set of numbers in each of these 2 locations. And that is what collaborative filtering is. So that's actually all we need. So rather than doing it in Excel, and show you the Excel version later if you're interested, because we can actually do this whole thing and it works in Excel. Let's jump and do it into PyTorch. Now, one thing that might just make this more fun is actually to know what the movies are, and MovieLens tells us in u.item what the movies are called, and that uses the delimiter of the pipe sign, weirdly enough. So here are the names of each movie. And so one of the nice things about pandas is it can do joins, just like SQL. And so you can use the merge method to combine the ratings table and the movies table. And since they both have a column called movie, by default it will join on those. And so now here we have the ratings table with actual movie names. So that's going to be a bit more fun. We don't need it for modeling, but it's just going to be better for looking at stuff. So we could use Data Blocks API at this point, or we can just use the built-in application factory method. Since it's there, we may as well use it. So we can create a collaborative filtering data loaders object from a data frame by passing in the ratings table. By default, the user column is called user, and ours is, so fine. By default, the item column is called item, and ours is not. It's called title. So let's pick title and choose a batch size. And so if we now say show batch, here is some of that data. And the rating is called rating by default, so that worked fine too. So here's some data. So we need to now create our, let's assume we're going to use that 5 numbers of factors. So the number of users is however many classes there are for user, and the number of movies is however many classes there are for title. And so these are, so we don't just have a vocab now, right? We've actually got a list of classes for each categorical variable for each set of discrete choices. So we've got a whole bunch of users, 944, and a whole bunch of titles, 1,635. So for our randomized latent factor parameters, we're going to need to create those matrices. So we can just create them with random numbers. So this is normally distributed random numbers. That's what rand n is. And that will be n users. Okay, so 944 by n factors, which is 5. So that's exactly the same as this, except this is just 15. So let's do exactly the same thing for movies. Random numbers and movies by 5. Okay, and so to calculate the result for some movie and some user, we have to look up the index of the movie in our movie latent factors, the index of the user in our user latent factors, and then do a cross product. So in other words, we would say like, oh, okay, so for this particular combination, we would have to look up that numbered user over here and that numbered movie over here to get the two appropriate sets of latent factors. But this is a problem because lookup in an index is not a linear model. Like, remember, our deep learning models really only know how to just multiply matrices together and do simple element-wise nonlinearities like ReLU. There isn't a thing called lookup in an index. Okay, I'll just finish this bit. Here's a cool thing though. The lookup in an index is actually can be represented as a matrix product, believe it or not. So if you replace our indices with one hot encoded vectors, then a one hot encoded vector times something is identical to looking up in an index. Let me show you. So if we grab so if we call the one hot function, that creates a, as it says here, one hot encoding, and we're going to one hot encode the value 3 with n users classes, and so n users, as we've discussed, is 944, right? Then so if we go one hot encoding the number 3 into n users, one hot 3, we get this big array, big tensor, and as you can see in index 3, 0, 1, 2, 3, we have a 1, and the size of that is 944. So if we then multiply that by user factors, or user factors, remember, is that random matrix of this size. So what's going to happen? So we're going to go 0 by the first row. And so that's going to be all zeros. And then we're going to go 0 again. And then we're going to 0 again. And then we're going to finally go 1, right, on the index 3 row. And so it's going to return each of them. And then we'll go back to 0 again. So if we do that, remember @ sign is matrix multiply. And compare that to user factors 3. Same thing. Isn't that crazy? So it's a kind of weird, inefficient way to do it, right? But matrix multiplication is a way to index into an array. And this is the thing that we know how to do SGD with, and we know how to build models with. So it turns out that anything that we can do with indexing to array, we now have a way to optimize. And we have a question.
There are two questions. One, how different in practice is collaborative filtering with sparse data compared to dense data?
We are not doing sparse data in this course, but there's an excellent course I hear called Computational Linear Algebra for Coders. It has a lot of information about sparse.
The Fast AI course. Second question, in practice, do we tune the number of latent factors?
Absolutely, we do. Yes, it's just a number of filters, just like we have in pretty much any kind of deep learning model. All right, so now that we know that the procedure of finding out which set of latent factors is the right thing, looking something up at an index, is the same as matrix multiplication with a one-hot vector. I already had it over here. We can go ahead and build a model with that. So basically, if we do this for a few indices at once, then we have a matrix of one hot encoded vectors. So the whole thing is just one big matrix multiplication. Now the thing is, as I said, this is a pretty inefficient way to do an index lookup. So there is a computational shortcut, which is called an embedding. An embedding is a layer that has the computational speed of an array lookup and the same gradients as a matrix multiplication. How does it do that? Well, just internally, it uses an index lookup to actually grab the values. And it also knows what the gradient of a matrix multiplication by a one-hot encoded vector is, or matrix is, without having to go to all this trouble. And so an embedding is a matrix multiplication with a one-hot encoded vector where you never actually have to create the one-hot encoded vector. You just need the indexes. This is important to remember because a lot of people have heard about embeddings and they think there's something special and magical, and they're absolutely not. You can do exactly the same thing by creating a one-hot encoded matrix and doing a matrix multiply. It is just a computational shortcut, nothing else. I often find when I talk to people about this in person, I have to tell them this 6 or 7 times before they believe me, because they think embeddings are something more clever, and they're not. They're just a computational shortcut to do a matrix multiplication more quickly with a one-hot encoded matrix by instead doing an array lookup. Okay, so let's try and create a collaborative filtering model. In PyTorch, a model or an architecture, or really an nn.module, is a class. So to use PyTorch to its fullest, you need to understand object-oriented programming because we have to create classes. There's a lot of tutorials about this, so I won't go into detail about it, but I'll give you a quick overview. A class could be something like dog or ResNet or circle, and it's something that has some data attached to it and it has some functionality attached to it. Here's a class called example. The data it has attached to it is A, and the functionality attached to it is say. And so we can, for example, create an instance of this class, an object of this type example. We pass in Sylvain. So Sylvain will now be in ex.a. And we can then say ex.say, and it will call say. And it will say, passing in nice to meet you. So that will be x. And so it'll say hello self.a. So that's Sylvain. Nice to meet you. Here it is. Okay. So in Python, the way you create a class is to say class and its name. Then to say what is passed to it when you create that object, it's a special method called dunderInit. As we've briefly mentioned before, in Python, there are all kinds of special method names that have special behavior. They start with 2 underscores, they end with 2 underscores, and we pronounce that dunder. So dunderInit. All methods in all regular methods, instance methods in Python, always get past the actual object itself first. So we normally call that self, and then optionally anything else. And so you can then change the contents of the current object by just setting self.whatever to whatever you like. So after this, self.a is now equal to Silver. So we call a method, same thing, gets past self, optionally anything you pass to it, and then you can access the contents of self, which you stashed away back here when we initialized it. So that's basically how the basics of object-oriented programming works in Python. There's something else you can do when you create a new class, which is you can pop something in parentheses after its name, and that means we're going to use something called inheritance. And what inheritance means is I want to have all the functionality of this class, plus I want to add some additional functionality. So module is a PyTorch class, which FastAI has customized. So it's kind of a FastAI version of a PyTorch class. And probably in the next course, we'll see exactly how it works. But it looks a lot like it acts almost exactly like just a regular Python class. We have an init, and we can set attributes to whatever we like. And one of the things we can use is an embedding. And so an embedding is just this class that does what I just described. It's the same as a linear layer with a one-hot encoded matrix, but it does it with this computational shortcut. So you can say how many, in this case, users are there and how many factors will they have. Now, there is one very special thing about things that inherit from module, which is that when you call them, it will actually call a method called forward. So forward is a special PyTorch method name. It's the most important PyTorch method name. This is where you put the actual computation. So to grab the factors from an embedding, we just call it like a function, right? So this is going to get passed here the user IDs and the movie IDs as two columns. So let's grab the 0 index column and grab the embeddings by passing them to user factors. And then we'll do the same thing for the index 1 column. That's the movie IDs, pass them to the movie factors. And then here, there's our element-wise multiplication, and then sum. And now remember, we've got another dimension this time. The first axis is the mini-batch dimension. So we want to sum over the other dimension, the index 1 dimension. So that's going to give us a dot product for each user. For each rating, for each user movie combination. So this is the dot product class. So you can see if we look at one batch of our data, it's of shape 64 by 2 because there are 64 items in the mini batch, and each one has this is the independent variables. So it's got the user ID and the movie ID.
And
sure.
Do deep neural network based models for collaborative filtering work better than more traditional approaches like SVD or other matrices?
Let's wait until we get there. So here's X, right? So here is one user ID, movie ID combination. Okay? And then for each one of those 64, here are the ratings. So now we've created a dot product module from scratch, so we can instantiate it, passing in the number of users, the number of movies, and let's use 50 factors. And now we can create a learner. Now this time we're not creating a CNN learner or a specific application learner. It's just a totally generic learner. So this is a learner that doesn't really know how to do anything clever. It just stores away the data you give it and the model you give it. And so since we're not using an application-specific learner, it doesn't know what loss function to use. So we'll tell it to use MSE and fit. And that's it, right? So we've just fitted our own collaborative filtering model where we literally created the entire architecture, it's a pretty simple one, from scratch. So that's pretty amazing. Now the results aren't great. If you look at the Movie Lens dataset benchmarks online, you'll see this is not actually a great result. So one of the things we should do is take advantage of the tip we just mentioned earlier in this lesson, which is when you're doing regression, which we are here, right? The number between 1 and 5 is like a continuous value. We're trying to get as close to it as possible. We should tell FastAI what the range is. So we can use Y range as before. So here's exactly the same thing. We've got a Y range. We've stored it away. And then at the end, we use, as we discussed, sigmoid range, passing in. And look here, we pass in star self.y range. That's going to pass in by default 0, 5.5. And so we can see, not really any better. It's worth a try. Normally this is a little bit better, but it always depends on when you run it. I'll just run it a second time while we're looking. Now there is something else we can do though, which is that if we look back at our little Excel version, the thing is here, when we multiply, these latent factors by these latent factors and add them up, it's not really taking account of the fact that this user may just rate movies really badly in general, regardless of what kind of movie they are. And this movie might be just a great movie in general, just everybody likes it, regardless of what kind of stuff they like. And so it'd be nice to be able to represent this directly. And we can do that using something we've already learned about, which is bias. We could have another single number for each movie, which we just add, and another single number for each user, which we just add, right? And we've already seen this for linear models, this idea that it's nice to be able to add a bias value. So let's do that. So that means that we're going to need another embedding for each user, which is of size 1. It's just a single number we're going to add. So in other words, it's just an array lookup. But remember, to do an array lookup that we can kind of take a gradient of, we have to say embedding. So we'll do the same thing for movie bias. And so then all of this is identical as before. And we just add this one extra line, which is to add the user and movie bias values. And so let's train that, see how it goes. Well, that was a shame. It got worse. So we used to have, that finished here, 0.87, 0.88, 0.89. So it's a little bit worse. Why is that? Well, if you look earlier on, it was quite better. It was 0.86. So it's overfitting very quickly. And so what we need to do is we need to find a way that we can train more epochs without overfitting. Now, we've already learned about data augmentation, right? Like rotating images and changing their brightness and color and stuff. But it's not obvious how we would do data augmentation for collaborative filtering, right? So how are we going to make it so that we can train lots of epochs without it overfitting? And to do that, we're going to have to use something called regularization. And regularization is a set of techniques which basically allow us to use models with lots of parameters and train them for a long period of time, but penalize them effectively for overfitting, or in some way cause them to try to stop overfitting. And so that is what we will look at next week. Okay, well, thanks everybody. So there's a lot to take in there. So please remember to practice, to experiment, to listen to the lessons again, because for the next couple of lessons, things are going to really quickly build on top of all the stuff that we've learned. So please be as comfortable with it as you can. feel free to go back and re-listen and go through and follow through the notebooks and then try to recreate as much of them yourself. Thanks everybody, and I will see you next week or see you in the next lesson whenever you watch it.